Hi guys. For those who just come in, we'll wait until 1:05, so maybe 4 more minutes, so that other students in the campus can actually have time to change to a room. Okay, again, for those who just come in to the room, we'll wait for 2 more minutes, so that it will be the official start of the lecture, just like the physical lecture and everything. Okay, so I think I'll start now. So once again, I'm really sorry that I have to arrange a Zoom meeting today. It's approaching the end of term. First of all, the school rooms are really busy, and it's getting more difficult to book room and time for a lecture, especially 2 hours, and with a seminar following. I'm really sorry that I have to make a Zoom lecture, and so let me just show you the what we are going to talk about today first. So if you, I don't know if you can see the screen. Let me stop sharing for a moment and share it again. Um, so I hope everyone can see the screen. Sorry, I'll be quicker. So the first thing I want to talk about is the exercise. So I think many of you haven't done the exercise, so it's only maybe every time maybe only one third of you. So although it's not really counting towards the final grade, so it's formative assessments, but it's really important that you catch up with the ideas, catch up with all the um, workings that we build on for the lectures. Otherwise, it will be getting further and further away from you. Okay, so it's getting more difficult to catch up as well. So if you haven't, so please try to catch up with the exercise. So if you have any questions, so post it on the discussion forum. So I just answered one question from discussion forum. So I haven't checked the last 2 days. So remember any questions, so post it on the discussion forum. I'll try to answer that as quickly as possible, or just send me an email. Okay, just drop me an email, quick email. Okay, so that's one important thing. And so today we are going to start another very important topic on the course, which is multivariate time series. Remember last week we talked about in the last lecture we talked about forecasting. So forecasting with the ARMA model is we basically try to find the best forecast first. So for best forecast at lag age is actually the conditional expectation on xt plus h based on conditioning on the information up to time t. Okay, so um, so this is important to remember that that's the always the best um, lag step h ahead forecast. Okay, I remember we use L, okay, L or H doesn't matter. So L step ahead forecast. So the is basically conditioning on information up to time t, the conditional expectation of xt plus L. And for ARMA model, this is actually easy to calculate. Okay, so um, we don't need to do the second best thing, which is use linear approximation, which we have done in the last lecture as well. We use prediction equations, remember? So how do we derive the prediction equations? So we basically assume a linear forecast first. Okay. So all these we have talked about in the second half of the last lecture. Okay, so this lecture we start with a new topic, which is multivariate time series. So let me share the. Uh, wait a minute. Sure, let me share with this again. Okay, so let me know if you can't hear me or if you can't see anything. Okay, so I have to minimize all the windows there in order to see what I'm writing myself. Okay, so okay, all right. So multivariate time series. Now, I don't know if I have explained from the start of the lecture, from the start of the course actually, what difference between multivariate time series and high dimensional time series. So in a nutshell, multivariate time series is actually not really large number of time series, but relative to the sample size, the dimension of the time series is fixed. Okay. High dimensional time series, on the other hand, relative to the sample size, the number of time series you are analyzing is actually diverging with the sample size. Okay. It can be diverged at a half a rate of sample size, zero point 0.1 of sample size, or square root of sample size. It's still diverging. Okay. So in those sense, they are high dimensional time series, not multivariate time series. So in multivariate time series, we usually talk about fixed dimension, okay, relative to the sample size. All right. So let's start from the beginning. Let's introduce some notation first. So it's basically the same notation, but this time xt, rather than being a scalar, is actually a d-dimensional factor. Okay. So xt is a d-dimensional vector. So d here is fixed. Okay. So for instance, d equals 2 is a bivariate time series. Okay. So we use this general notation. So x1t, x2t, and all the way up to xdt to denote all the d different variables in the vector xt. Okay. So again, so all my vector notation is actually column vector. So I need to take a transpose there. And the first thing we want to talk about is remember in univariate time series, what we talk about. We talk about the building block of very simple time series, and the simplest of time series is weakly stationary time series, right? So let's revisit weak stationarity, but this time is for multivariate time series. So weak stationarity is very similar to univariate time series. You can say it's basically the same, but this time you have to consider a multivariate mean mu. So it's a factor of mean. So it's mu1, mu2 up to mu d, okay, for expectation of x1t, x2t up to xdt. And all of these expectations are finite, okay? So a factor is finite means all its components are finite, okay? So i.e. all components are finite. So that's what I mean by a factor is less than infinity. The second point is a little bit different, but you'll see it in a minute. So we need to define a matrix gamma, gamma ht. Now this gamma ht in our lecture notes we define as the covariance between xt and xt plus h. Okay, this is the same as our scalar definition, right? The scalar counterpart is basically the same covariance of xt and xt plus h, but now xt is a factor. So what do I mean? What do I mean by this covariance? I would guess that some of you may not know the definition. So here is the definition of a. This is what we call the covariance matrix, and this covariance matrix is basically well xt minus mu first. Mu is the expectation of xt, right? And then multiply with xt plus h minus also the mean mu is actually expectation of xt plus h, but under weak stationarity is also mu. And multiply with its transpose, okay? So a column factor multiplied with a row factor is a matrix, okay? So it's the expectation of a matrix. So this is called the covariance matrix, Okay, so it's a lag H covariance matrix. But this definition needs to be defined better, actually. You'll see why in a minute. So this matrix has finite elements. So it's a D by D matrix, right? So all the D by D elements are finite and are also functions of H only. So that's important, right? It's only function of the lag H. And so gamma HT will be independent of time t. So it's just a function of H. Okay. So let me save this. So if you have any questions, let me know. Okay. Just have a shout or type it on the chart. I'll try to call in a fixed time interval check the chart. Okay. So this is the definition of multivariate time series. Well, one important thing actually arises. Okay. So I have defined gamma H as the covariance between xt and xt plus h. Now, how about the covariance between xt and xt minus h? Well, in a scalar case, you can say, okay, because it's weakly stationary already, covariance of xt and xt plus h and xt minus h, well, they're the same, right? It's a function of h, okay, after all. Well, in multivariate cases, it's not that easy. So there's a nuance here. Now, covariance of xt and xt minus h, remember, using first principle, the definition of it, this is xt minus mu, and xt minus h minus mu transpose. Okay. So this matrix is actually the transpose of a bigger matrix. So it's a transpose of this matrix. So xt minus h minus mu, and then xt minus mu transpose. Transpose, okay? So it's the transpose of the inside matrix. Now, the inside matrix, if you look closely, well, this is actually the definition of gamma H. It's the definition of gamma H when T is replaced exactly by T minus H. So this is actually gamma H, not exactly gamma H, but gamma H transpose, okay? And if you ask, well, is gamma H symmetric? Well, there's no reason for it to be symmetric unless H equals to 0. When H equals to 0, this is exactly the variance covariance matrix. Then this is symmetric. When H is not 0, gamma H, there's no reason to be symmetric at all. Okay? So it's not equal. Gamma H transpose is not equal to gamma H. Okay? So this is one thing that you need to be really careful. Okay? And there's also another thing. So this definition of gamma HI follows in the lecture notes. So in R, there's also one way to calculate gamma H. We'll see in a minute. So I'll talk a little bit more first when I introduce the vector armor model. But in R, this is defined actually as, so let me put a tilde. So this is in R, okay? So gamma H tilde is actually the covariance of XT and XT minus H for H larger than or equal to 0, okay? So in R is a little bit different from what we have in the lecture note. So what we have in the lecture note is xt plus H for H larger than 0. Here is xt minus H, okay? So it's basically the transpose of what we defined in the lecture uh, in the face of what we have just calculated, okay? Gamma H transpose is not gamma H, okay? It's not, yeah. But what is actually equal here is actually in fact gamma H, gamma minus H is actually gamma H transpose, okay? So this will be always be correct, all right? Gamma minus H is gamma H transpose. So whenever you consider a negative lag, it basically transpose your matrix, all right? So that's one thing that you need to bear in mind. So that's very important. And let's export this as well. So this is the second page. Okay. So now I want to formally introduce the vector version of the armor model. So we don't need to start from white noise like lecture one. So it's basically the vector armor model. Or the short form is VARMA, so VARMA, of order P and Q. Now, this definition is very similar to the scalar version. So your xt equals to a constant alpha, a constant factor, remember? So a constant factor plus phi 1 xt minus 1 plus all the way up to phi p xt minus p plus epsilon t plus theta 1 epsilon t minus 1. So it's all the same. After defining the AR process, we define the MA process, but they are all factor version. Here, your epsilon t is white noise. Now, this time it's a multivariate white noise, okay? So it still has a mean 0, but the covariance matrix, the covariance is replaced by a covariance matrix, okay? So the variance covariance matrix is from sigma square becomes a matrix gamma, okay? And these phi j, theta j, they are all actually d by d matrices. They are not scalar anymore. They're d by d matrices, the most general version. So phi p, theta q, they are not zero matrices. Is this definition is the same as the scalar version, okay? So phi p and theta q are matrices to define the order of this vector armor model. So you can see it's a very complicated process, okay? And your epsilon t is a um, white noise. So Wn is white noise of dimension d. And covariance of epsilon t and epsilon t plus h will then be the zero matrix. Okay, so that was we mean by a white noise. Okay, for positive h, for negative h, they are all zero. Okay, and the variance covariance matrix for variance of epsilon t is gamma. Okay, and this matrix has finite elements, so that's what we mean by multivariate white noise. All right, and if you can remember for this variance covariance matrix, so variance of epsilon t is just the covariance between epsilon t and epsilon t. And this is just epsilon t transpose taken expectation. Okay. So all these are, if you're very familiar with multivariate random variables, that's fine. But I'll guess that some of you may not be familiar. So I need to redefine many things that may not be familiar to you. Okay. So variance covariance matrix, there's expectation of epsilon t transpose. So one question now, okay, so vector armor, no, nothing special. It's very, very similar to the scalar version, but except that the parameters are now parameter matrices, not scalar parameters anymore. Okay, so when d increases, the number of scalar unknown parameters actually increases quadratically with dimension. Okay, so the dimension increase, that means you have way more parameters to estimate than the scalar version of the armor model. Okay, so that's one thing to remember. Let me export this as well. So now, after introducing this vector armor model, so I'll introduce the condition for stationarity for the whole system of this multivariate time series before we look at a little bit of examples, okay, in R. So, uh, where's the page number? So, condition for stationarity. Now, we are talking about the vector armor model, okay? So, the vector armor model can actually still be written as the characteristic polynomial version of it, okay? But this time, the characteristic polynomial is a little bit different. So this polynomial actually contains how many polynomials? There are d by d of them, okay? And by the first look of it, it may be a little bit confusing if you think about it, but this will be cleared up, okay? So let me finish the writing of the most general form of the vector armor model first, okay? So this is the in terms of the characteristic polynomial. So first of all, what is ID? Now ID is the just the d by d identity, okay? The d by d identity matrix. Okay, so it's let me. And the whole Oops. What am I doing? Oh, what's happened? I don't know what happened. So let me rewrite this again. Okay, so I'll make sure this mistake won't happen again. Goodness. So condition for stationarity. So let me quickly write down the multivariate version in terms of the characteristic polynomials. So this part you should have no problem. It just becomes a multivariate version. Now remember ID is the d by d identity. And the whole thing here is actually defined as the AR characteristic polynomial. And this one, for the same token, similar to the scalar version, this is the MA characteristic polynomial. Okay, so you can see that the polynomials are now not just one polynomial, but how many of them? There are actually d by d of them. So it's a matrix of polynomials. So it's a d by d matrix, and each element in the d by d matrix is a polynomial in B. Yeah. And what we need for condition for stationarity for the system is we need to look at this time. It's very similar to phi z equals 0, but is the determinant of phi z equals 0. Okay. So this is not absolute value. So when it's similar to the absolute value, but when it's the matrix as the inside, and this is actually the determinant of the matrix. So this is the determinant. So let me move a bit. So again, if all roots, now all roots of this determinant of psi z equals 0 are outside the unit circle, then your xt as a factor Armour model of all the P and Q is weakly stationary. So once again, the MA characteristic polynomial or polynomials here won't do a part in stationarity. It's all about the AR characteristic polynomials. Okay, but let me uh, let me just finish with all the definition first before I give a very concrete example. Then I hope that will remove any doubt and any un uh things that is not clarified. So phi inverse B exists, just like the scalar version. It means your xt, you can apply phi inverse B. So you can consider it as a matrix polynomial, matrix operator inverse. Okay. on both sides. So it's alpha plus theta b epsilon t. Okay. So it's basically just constant factor. And then plus the sum of psi j epsilon t minus j larger than or equal to 0, where your sum of the largest eigenvalue of psi j from 0 to infinity, is actually finite, okay? Where your this norm of psi j is actually the basically largest singular value, okay? And this is the eigenvalue, the largest one of psi j transpose. When we talk about largest eigenvalue, psi j transpose, psi j transpose, psi j, they will coincide, okay? They have the same eigenvalues for the largest one, okay? All right. Um, so everything is fine, and deep psi j basically is again a d by d matrix, okay? So the largest eigenvalue of this, largest singular value of this d by d matrix, when summed together, is finite, okay? When sum order lengths, j from 0 to infinity, okay? And so let me very quickly give you the simplest example possible I think of, which is a bivariate example, so that hopefully will clear things up for you. Well, I think I skipped 3, okay? I'll change back to, yeah, this should be 4, right? Yeah, and this should be 5. So let me quickly give you an example in this page. Now, the easiest example I can think of is bivariate time series. So let's say this bivariate time series is x1t, x2t, and xt is actually defined by alpha plus phi xt minus 1. So it's a factor AR1 model. Okay. Your epsilon t is a, this time is a multivariate normal with mean 0, and variance covariance matrix equals to sigma square times the identity matrix, the 2 by 2 identity matrix. So this, let's define this alpha as alpha 1, alpha 2 transpose. And let's define this epsilon t as epsilon 1t, epsilon 2t transpose. Okay, so they're all column factors. So therefore, your xt is a factor AR1 model. Let's say phi equals to maybe this particular matrix. Okay, so 0 0.8, 0 0.4, 0.2, maybe 0.7. Okay, so that it certainly can have my negative values. I just put positive values in here. So let's look at the separate equations for x1t and x2t first. Okay, so x1t here will actually be then alpha 1 plus zero point 0.8 x1 t minus 1 plus zero point 0.4 x2 t minus 1 and then plus epsilon 1t. And then x2t, so it's alpha 2 plus zero point 0.2 x1 t minus 1 and then plus zero point 0.7 x2 t minus 1 and then plus epsilon 2t. Okay, so that's the system. Now, if I give you these two equations, so I ask you write it back as a factor system, like xt equals alpha plus phi, xt minus 1 plus epsilon t. So you need to be able to define what alpha is, what phi is, etc. All right. So vice versa, like in this example, if I give you this system, so I ask you to write these individual equations for individual components. So you need to be able to do that. All right. Okay, so with this system, so what do I want to do? So this is a system, right? Now consider the AR characteristic polynomial. This is a factor AR1 model, okay? So a bivariate uh, factor, so it's I2, the 2 by 2 identity, minus the matrix phi times Z, right? So Z is a scalar, phi is a matrix, so well, they are multipliable, but it is exactly this definition. Okay, so this is 1, 1, 0, 0 on the orthogonal minus phi times that. So every element in the AR1 matrix phi 1 should be multiplied with z. Okay, so 0.8 z, 0.4 z, 0.2 z, and then 0.7 z. Okay, and this will be simplified to 1 minus 0.8 z and then zero point 0.4 minus 0.4 z and then minus 0.2 z and then it's 1 minus 0.7 z. Okay, so I hope this clear any nuance up. So basically the backward shift operator is replaced by the polynomial set, and this is multiplied into every element of the coefficient matrix. Okay. Now then, what is the determinant of this phi set? Well, the determinant of a 2 by 2 matrix, so you should be able to calculate. Okay. So in exam, I will not ask you more than 2 by 2 actually. If you see 3 by 3 matrix, that means there's some simplification that you should see. That leads to just calculation of 2 by 2 determinant. Okay. All right. So phi set equals to the determinant. So first of all, is basically 1 minus 0.8 z multiplied with 1 minus 0.7 z, right? And then the minus the product of the off diagonals, 0.4 z, minus 0.4 z times minus 0.2 z. So this 0.08 z square. So if I'm gonna simplify that, so that's 1, and then some minus 0.8 minus 1.5 z, and then plus 0.56 z square minus 0.08, so that's plus 0.48 z square. So set it to 0. Now we can calculate the roots. So therefore the roots are. So I'll ask you to do this exercise for me. So minus b plus or minus square root of b squared, 2.25, minus 4 times A is 1, and then C is, A is 4.48, and C is 1. So 4 times 0.48. And then divide by 2A. Okay, so 2 times 0.48. So you can see, of course, these roots are real, but are they larger than 1 or smaller than 1? So you calculate, okay? And then determine if the system is actually stationary or not. So this is the way to determine if the whole system is actually stationary or non-stationary. Okay. So, and then you may ask, how about invertibility? Well, it's similar. After all, stationarity or invertibility is the ability to invert the operator. Now, the operator is a matrix itself, but doesn't stop us from inverting them. So, similar criterion for invertibility. So it's basically see the roots of theta set equals 0. The determinant of theta set equals 0 are all outside the unit circle or not. All right. So this is basically the stationarity and actually invertibility as well. All right. So let's look at some very quick examples before we let me before I forget. So let's save this first. Okay. So let's save this. I'll change back to page number. So this should be page 5. Okay. So let me share my screen for the R first. Okay. Where's my R? Okay. So everyone can see my R Studio. So this is I haven't loaded anything yet. So in your Moodle, so there's a R script called Granger causality. So I don't know if we are quick enough to talk about Granger causality, but at the top part of it, there's an example that you can copy. At the same time, from the lecture note on page example 4.6, this is page 76. There's also an example that you can copy and try to plot. Okay, so the library. Okay, so let me copy this first. So everyone can see this. Um, Basically, the library is multivariate time series or MTS that we are using. We will not go too deep in it. So we basically will look at something called a cross correlation plot. Okay. So the cross correlation function plot, and that is a CCM command you see here. I will introduce in a minute. So for now, I'll actually load the library and then simulate this vector armor model. Okay, so this vector armor model with order 1 and 1. So it's a Varma 1 model, and the P1 is phi 1, and TH1 is theta 1. Okay, so the sig matrix SIG is actually the variance covariance matrix gamma for the epsilon T for the noise. Okay, and so what is P1 here? So this P1 is just a bivariate a bivariate system. So it's a 2 by 2 matrix. So you can see this certainly is not symmetric. Okay, so it's just a coefficient matrix. There's no reason for it to be symmetric at all. So what is theta 1? Your theta 1 is diagonal matrix. Okay, so that doesn't matter particular, but it's just an example. Okay, now for the variance covariance matrix, then of course this sig matrix, no, this sig matrix of course has to be symmetric. Okay, this has to be symmetric. All right. So I have simulated M1. So this basically created all the simulated series. So how do we actually plot it? Well, if you look at the output of M1 here, the Farmer sim function. So there's a series and there's the noises. Okay. So you can plot the simulated series. Also, you can plot the white noise. Okay. So there's actually two set of series generated for you. Okay, one is the factor white noise series. It's basically Gaussian white noise if it's simulated from here. Okay, so if you want to generate Gaussian white noise, well, you can actually uh, use a Varma sim function as well. All right. So how to plot this series? The best function to plot this series is actually this MTS plot, so multivariate time series plot. Okay. And M1 series, you call the series inside M1, right? And if you plot this, so you plot basically both, sorry. Um, yeah, I don't know what happened. So let's plot it again. So I hope everyone can see the plots. Okay, so this x12 x1t on the upper plot and x2t on the lower plot. Okay, so you can see both of them are complicated functions, complicated time series uh, defined basically intertwined with the two time series involvement getting involved in the future value of both time series x1t and x2t. Okay, so this system appears to be stationary, so you should check. In fact, if it's not stationary, R will actually tells you again with error, with warnings. Okay, so this system is stationary. Try to check it. Try to check with this example as well. Okay, this is again in the lecture note, page 76. Okay, so uh, I will continue with this example in a minute. So I'll give you 5 minutes break. Okay. So please come back at exactly 2 o'clock, and then we'll continue with the second half of the lecture with more examples and more introduction to some new ideas. Okay. Okay. So, for the second half of the lecture, so we'll talk about the some generalization of the concepts that we have done in the scalar time series as well. Okay. So for first half, we talk about extension of the weak stationarity, white noise, and also the vector armor model. How do we determine stationarity in the multivariate system of vector armor model? And so for the second half or so, we want to start off with a something that we have also done in this scalar version, which is the Walker estimator. Okay, so let me share my screen once again. Okay, so I have saved this. So let me start new page talking about this Walker estimator. So this is your walk estimator. Remember when we talk about it, is concerned with the AR model. So this time, by the same token, so we are talking about the vector ARP model and the Walker estimator. So your Walker estimator. Now let's define the time series first. So if xt follows a vector ARP model and is defined by alpha plus phi 1 xt minus 1 plus all the way up to phi p xt minus p plus, again, a multivariate white noise epsilon t with mean zero and covariance matrix gamma. Okay. So remember, how do we determine the York estimator? We first calculate some moment equations first, right? So here we do the same thing. We take covariance with xt minus h for h larger than 0. So we assume that covariance of xt and xt minus h is once again this gamma h transpose, okay? Our gamma h is xt plus h. So uh, when we talk about xt minus h covariance, that's gamma h transpose. All right. And of course, by writing this, I assume stationarity. Okay, so this is implicitly assumed in here. Now with this, then the left-hand side is, okay, gamma H transpose, which equals to the covariance between phi 1 xt minus 1 and then xt minus h, and then plus all the way up to covariance between phi p xt minus p and xt minus h. Now, you may ask, so there should also be a covariance of epsilon t and xt minus h. This is the same, okay? So covariance between future epsilon t and past xt, they're zero, okay? Because stationarity means your xt's can be expressed as an MA infinity up to the time defined. So xt minus h is an MA infinity up to time t minus h. Okay. So all the past epsilons defined up to t minus h Of course, it's uncorrelated with epsilon t. Okay, so this will be 0. And what are these? This you need to be a little bit careful this time. So this, let's look at the first principle. What is the definition of this? So this is phi 1 xt minus 1 minus mu. And then it's xt plus h minus mu transpose, right? That's the definition. So this will be phi 1. Actually, gamma h minus 1. And not gamma h minus 1, but gamma h minus 1 transpose, okay? So the phi 1 on the left hand multiply, a matrix multiply on the left hand side can actually be taken out onto the left hand side, okay? And what's left with is um, covariance between xt minus 1 and xt minus h, okay? So it's minus, so it's the transpose of the covariance matrix. The time lag is h minus 1, okay? So you need to be really careful about will there be a transpose or not. So it all depends on how you define your covariance of xt and xt plus h or xt minus h as gamma h, okay? So this will be, well, phi 1 gamma h minus 1 transpose plus similarly phi 2 gamma h minus 2 transpose plus all the way up to phi p gamma h minus p transpose. Your h runs from 1 to etc. Okay. And let me do this on the same page. Now you have this system of equations, right? You have this system of equations. These are the Walker equations, the multivariate version of the Walker equations. Then your gamma h uh, we should write this. Let me pull back down a bit. So it's all in transpose, okay? So let's we transpose it, okay? Let's take transpose on both sides. So gamma h equals to gamma h minus 1 times phi 1 transpose plus all the way up to gamma h minus p times phi p transpose. Okay, so we transpose it. That is, if you put them into an even larger system, so let's say gamma 1, gamma 2, all the way up to gamma p on the left hand side. So it will equals to, now this is basically the same as when we write Walker equation into a matrix system. This is writing the Walker equations, multivariate Walker equations, also into a matrix system, okay? But this time it's a block matrix. So it's gamma naught. When H is 1, it's gamma naught, phi 1 transpose, and then plus gamma 1, gamma minus 1, right? And gamma minus 1 is gamma 1 transpose, gamma 2 transpose, etc. up to gamma p minus 1 transpose. And then when h is 2, so this is gamma 1, and this is gamma 0, and then gamma 1 transpose up to gamma p minus 2 transpose, etc., etc. So this is up to gamma p minus 1, gamma p minus 2. So gamma p minus 2. gamma p minus 3, etc., back all the way back to gamma 0. And this will be multiplied with, of course, phi 1 transpose up to phi p transpose. Phi 1 transpose up to phi p transpose. So that's the whole system of equations. So if we call this a big, it's not a vector anymore, it's a matrix, but it's a long matrix. So if we call this gamma bracket p, and if we call this large sigma p, and if we call this, let's say phi bracket p, then the whole system means that this phi bracket p, this is our parameters that we need, right? It will be sigma p inverse multiplied with gamma bracket p, okay? So apart from the fact that we need to be careful about, well, this gamma h or gamma h transpose, so this has to be clarified. You have to have a uh, very much 100% clarity in your mind. Is it the original definition of your gamma h, and then you go through with it in taking covariances. Then you will arrive at the estimators. Okay, is basically the same as arriving to the estimators for the Walker estimators. Okay, in the scalar version. So you finally, if your data, so if your data is x1 all the way up to x capital T, then we can estimate gamma h to be 1 over t, the sum of t from 1 to t minus h, xt minus x bar, and then xt plus h minus x bar. That's our definition. Remember, it's xt and then xt plus h transpose. Okay, so that's the transpose here. My transpose. So let me write it more like a transpose. Okay. And your x bar is basically the same. So x bar is t inverse sum of the xt's. All right. So the problem for this is really huge system. Okay, when d is 2, well, when d is 2, then you can see that this is already gamma naught is 2 by 2, gamma 1 is 2 by 2. Okay, so it's a 4 by 4 matrix already. So a medium matrix. When d is 10, then every matrix is a 10 by 10 matrix, right? So gamma naught, gamma 1 up to gamma p minus 1. If p is even p is 1, even p is 1, even p is 2, then so you see that this is already a very huge matrix. Okay, if you're considering a vector AR model with a large lag, okay, then your dimension better be not very large, maybe 2 or at most up to 3. Okay, so if you're considering a complex system with a lot of variables, so you rarely see that people use a vector armor model. And this is the reason, because as your dimension increases, it will require way too much data to actually estimate the whole system correctly, because there are too many unknown parameters. If D equals 10, then each coefficient matrix is 10 by 10, so 100 unknown parameters. All right. So you don't want to do that. Okay. So let me introduce. So we have plotted the simulation of the vector armor model, right? How about the sample version of it? You remember in the scalar version, so we actually have defined the sample version quite successfully using the sample version of ACVS and sample ACF. Okay. And then we plot them and try to identify order, etc., etc. Okay. So that's the baseline for actually looking at the data in a more systematic way. So how about for the multivariate time series? Is there a similar tool for looking at different lags? Okay, so the answer is of course there is. And this will be the sample CCM. Okay, so let me write down here. And then we will see some example in R. So the sample CCM, so CCM stands for cross correlation matrices. So it's basically in parallel to the ACF, the auto correlation function. Okay, here in a multivariate version, we name it as cross correlation matrices. So why is it cross? It's because there are more than one component, of course. Different component can have covariance as well at different time lags. Okay, so that complicates the matter. So cross covariance matrices, and we are talking about for stationary time series. Okay, for stationary system. Is we have defined this before. So this is gamma h, which is expectation of xt minus mu and xt plus h minus mu transpose. Okay. So we define our gamma h this way, where your mu is just the multivariate mean of xt. All right. So the sample version, what's the sample version of it? If we have data, sample version is just what we have seen before. So this is 1 over t. Sum of this. This should be an absolute value of h. So we need to make sure this is positive. So it's xt plus h minus x bar transpose, where your x bar is the usual sample mean. Okay. So this is the cross covariance matrix. So this is CCM. How about cross correlation? In the plots that we are going to see, they're all cross correlation, not cross covariance. Okay. Well, as the name suggests, it has to be relative to corresponding variances. So we write CCM, and in R, the CCM function corresponds to cross correlation matrix. the plot of sample cross correlation matrix. So that's the CCM function in the MTS package, the multivariate time series package in R. So at leg H is defined as, so let me put a little bit up, row H as a function, as a matrix. So let me write down the formula first, okay? Half, and then multiply by gamma H, and then multiply with, again, this diagonal matrix, a half. Minus a half, okay. So first of all, what is di? DIAG, so DIAG of a matrix A is just a diagonal matrix with the diagonals retained. So if it's a n by n matrix, so it's A11 up to ANN on the diagonal, and then 0, everything else. Okay, so that will be the definition. And gamma naught here is what? Gamma naught here is the variance covariance matrix for xt. Okay, so ultimately, this is what? This is in an element-wise sense. The ij entry of this row H is what? Is the ij entry of this gamma H, the cross covariance matrix, divided by the square root of the ii entry of gamma naught and jj entry of gamma naught. Okay, multiplied together. So gamma naught ii entry, and then gamma naught jj entry. So I hope this sounds familiar because that's exactly the correlation between the ith component and jth component should be. Okay, so that is the cross covariance between the ith component and jth component, and then divided by their respective variance square root. That is the standard deviation for the ith component and the standard deviation for the jth component. Okay, so this definition of the matrix is exactly the same, basically akin, similar in parallel to the definition for the scalar version of cross correlation of two random variables. Okay. So sample version, of course, very similar then. Sample version. This is the population version, right? So sample version is which hat equals to di minus a half gamma naught hat. And then gamma h we replace by gamma h hat. And then it's the same here again. So I write minus a half on the diagonal. It basically means is the square root of the diagonal matrix. Square root of a diagonal matrix is basically the diagonal matrix of square root, right? And then take inverse. So it's basically the inverse square root of the diagonals of gamma naught hat. All right. So that's the definition. And let's have a quick look. So let me save this first again. Okay. So let's have a quick look at the R Studio again. So in R, Now, you can see the previous example in the lecture notes. Copied it here. So we have simulated a vector armor 1 model. It's a bivariate. Okay. So phi 1 and theta 1, they are all 2 by 2 matrices. Now, I have the plot here, but what about the sample cross correlation matrices? Okay. So here is a CCM function for the bivariate time series, and the number of legs I want to plot is 36. Okay, so I can change it, of course. So here in the lecture notes, I plot 36. So I hope all of you can see the plot. I've zoomed in the plot, so hopefully you can see that. If you can't, let me know. Okay, so I've zoomed in the four plots. So it's a 2 by 2 plot. Okay, so there are four plots stick together in one panel. What is the top left panel? The top left panel is the cross correlation function. It's basically the autocorrelation function plot for the x1t for the first component time series. And the lower right corner is the ACF plot for the second component. All right. But what is the top right plot? The top right plot, you can see that at leg 0 is not 1 because it's calculating covariance of, it's basically sample version of covariance of x1t and x2t. Okay, x1 cross correlation between x1t and x2t, cross correlation. And then on the again on the top right plot, let's focus on the top right plot. What is the stick at leg 1? What does it mean? Okay, so I may ask you these questions. Okay, so you pretty need to make sure what exactly all this means. Okay, so on the top right plot, what is the meaning of the stick at leg 1? What does it mean? It means is the sample correlation between x1t and x2t minus 1. Remember in R we use definition covariance of xt and xt minus h, not plus h. Is covariance of xt and xt minus h. Okay, so the leg 1 stick is covariance sample correlation of x1t and x2t minus 1. By the same token, at leg 5 of the top right plot, it depicts the sample correlation of x1t and x2t minus 5. Now, let's change our focus to the bottom left plot. Now, for the bottom left plot, what is leg 0? Is the sample correlation between x2t and x1t. And you may say, hey, wait a minute. Sample correlation between x2t and x1t, of course, it should be the same as x1t and x2t sample correlation. And if you look at leg 0 on the top right plot and bottom left plot, they are exactly equal. Of course, they should be equal because their meaning uh, is correlation between x1t and x2t. Sample correlation between x1t and x2t. Of course, they're interchangeable. But then let's focus back on the bottom left plot. How about leg 1? Is the bottom left plot of leg 1 the same as top right plot leg 1? No, they are not equal. There's no reason for them to be equal at all because the meaning of leg 1 stack at the bottom left plot is the sample correlation between x2t and x1t minus 1. By the same token, okay, at leg 10, let's look at leg 10 on the bottom left plot. Okay, it's also not the same as the leg 10 at top right plot. The meaning of that is correlation, sample correlation between x2t and x1 t minus 10. Okay. So they're different, except at lag 0. Otherwise, in general, they will all be different. Okay. All right. So I hope I've explained this clearly, and you need to know the meaning of these plots. Okay. And looking for these plots, well, looking for these plots, so the x1t looks like an x2t, so both have their sample ACF cut off at a very large lag. For X1T, maybe cut off at lag 3 or lag 2. But beyond that, you can see that there's a wave-like pattern. You can see that, right? For X1T, for the top left plot, for X1T ACF. Okay. Whenever you see these wave-like stakes, even if they are marginally within the dotted band, you should be careful. So it means that there's some more complicated dynamics is going on rather than just, okay, maybe it looks like AR2. Well, it's more than that, okay? And for X2T, of course, it cut off at like maybe 19, 18, okay? So if these large lags, that means maybe the dynamics is a little bit more complicated than you thought, okay? So remember, the dynamics we generate is actually intertwined, okay? It's a system. X1A and X2T, the definitions are intertwined. Okay. So again, let me know if you have any questions. Okay. So let's introduce, let me share back the Microsoft whiteboard. So we have say this page already, right? It's page 7. Okay. So I hope I explained everything clearly. If you find it a little bit slower than usual, it's intended because it's the first time I introduced multivariate time series. Okay. So it's a continuation of this CCM. Okay. So consider if XT is a factor MA model. Now this time it's just MA, where Q is larger than 0 or equal to 0. If Q is 0, that means it's just a factor white noise. Okay. So your VMA 0 is factor white noise. Okay. So with XT a factor MA, so we have some um, asymptotic results that you need to know. So there are basically only 3 of them. One is a generalized Young box statistic, which I'm going to talk about in a minute. The other 2 is actually similar to the scalar version we have introduced. So for row head L, the IJ entry of row head L, okay, so let L uh sample let L auto correlation matrix, okay. The IJ entry actually is asymptotically similar to this value, okay. So it's V from 1 to Q, row VII, and then row VJJ entry, okay, where your L has to be can be larger than Q, okay. So if your lag is larger than the vector MA model, then asymptotically the variance of each component in the sample correlation matrix, the leg L sample correlation matrix will be like this. Okay, so it's basically similar to this formula, which involve the leg 1, leg 2 up to leg Q population autocorrelation matrix. Okay, and it's the II entry and the JJ entry of it. If you consider the sample variance of the leg L uh, sample autocorrelation matrix at IJ entry. Okay, so this, if you check back at the scalar version in much earlier in the lecture notes, so this is in parallel. Okay, and in particular, if Q is 0, that is XT a white noise, a multivariate white noise. Okay, then we have this, the variance using the above. It will be 1 over t, and then 1 plus 2 times the sum of all these row VII, VJJ, and they are all 0. Leg 1, leg 2 up to leg Q, okay? They are all 0 because it's a white noise. Or the leg 1 up to leg Q entries, these autocorrelation matrix for this white noise, of course, is 0, except leg 0. So it's a 1 over t. And this explains the dotted band. So if you remember, we just look at the 4 plots. Each plot have a dotted band, okay? That dotted band is the same as ever. 1.96 divided by square root of t. So it makes sense for the top left and bottom right plot because they are ACF of x1t and x2t respectively. But what about the off-diagonal plots? They are covariance between x and x1 and x2, basically, at different legs. Okay, so y also use 1.96 divided by root t as the dotted band. So this is the reason. Okay, so this is one important result, asymptotic result that I want you to know. So can use plus or minus 1.96 divided by square root of t. This as an indicator to test. Of course, it's an eyeball test if xt uh, looks like a white noise. Okay, a multivariate white noise basically. So you need to look at all 4 different plots. Okay, so all 4 different plots, they look like white noise if it's a multivariate white noise. Because multivariate white noise, all the row V is 0 for V larger than or equal to 1. Okay, that means you need to look at the 4 plots. The 4 plots correspond to entries in this row V. Okay, at different legs, of course. Okay, so let me know if you have any questions. Okay, so let me write another result that you need to know. And this is the generalization of the Young-Borg statistic. So we introduce QKM equals to this t squared So let me write down the formula first, okay? So, okay. So this is the formula, and you know gamma hat L, and basically it's just the sample or covariance matrix at leg L. Okay, and what is TR? TR is the trace of a matrix. The trace of a matrix is the sum of the diagonal values. Okay. Usually, trace will be applied to square matrix, but you can apply to a rectangular matrix, no problem. You just sum all the uh, diagonal values, AII, okay? As long as I is equals to, it's not AIJ, but AII, okay? I is equal. So this can even be applied to a rectangular matrix, but vast majority of times, when we talk about trace of a matrix, that matrix usually is a square matrix, okay? Okay. So this is the Young-Ball statistic, and well, look quite a little bit different from the Young-Ball's P statistic for scalar version. Remember, this statistic is for what? Is for testing if your time series is look like a white noise. Okay, so if let's think about it for a moment. If it's a perfect white noise, we're summing L from 1 to M, excluding L equals 0. Okay, so L from 1, if gamma 1 hat is a perfect estimator, then gamma 1 hat is 0 if it's a white noise. By the same token, all gamma L are 0 actually, if they are all perfect estimators. So this statistic will be identically 0. Identically 0 if you have a white noise and everything estimated perfectly. Okay. So if the value of this QKM is small, then it indicate basically is a white noise. If it's excessively large, then it indicates that, okay, maybe it's not a white noise after all. Okay, so what is small and what is large? Here is the asymptotic result of what is QKM is. So if your null hypothesis is gamma L equals to 0, for all integers L larger than 0, and with xt normally distributed, so the asymptotic result does require normality of the data, then your QKM is actually going to a chi-square distribution. Again, this time to a degree of freedom m times n squared. Okay, so the degree of freedom is getting very large when the dimension is large. Okay, under h naught. So your xt is of dimension n. Okay, so this capital N here. So what is small? What is large? Asymptotically, it is determined by this chi-square distribution. Okay, so let's look back. Let's save this first. Okay, so let's look back at R. Okay, so let's share this. Uh, okay, so here we have plot the CCM. All right, and oh, sorry. And lastly, if you press enter, it will actually plot significance plot of CCM. Uh, this is actually a variation of the Young-Box peer statistic I've actually introduced. So the Young-Box peer statistic I've introduced is actually contained in this function MQ. So MQ of the data series. So MQ, the data series is M1 series, right? So this will be the Young-Box peer statistic. So you can see the QM, the degree of freedom, p-value. So all p-value is zero. P-value is zero. That means what? That means you reject the null hypothesis that these uh the corresponding uh lag M matrix is zero. Okay. That means if you look at the whole plot, the p-values, we consider all the lags here up to 24. So it's still all very small. Okay. That means what? That means at no point is these time series having zero lag L correlation matrix. Okay, at least that's what the test is telling us. And in fact, if you think back about it, of course, this is to be expected because this is a vector armor model. After all, it's a vector armor 1-1 model. Okay, so of course, no time series there look like a white noise. If you want white noise results, so if you look back at the M1, there's noises. Okay. So if you plot MTS, plot M1 noise. So here are the noises generated. Okay. These are the generated noises. They are all white noise. Okay. So if we do the Young-Box statistics on the generated noise, what will happen? So you can see that at least for the first few lags, they are all above the blue dotted line, okay, about 5%, okay. As lag increases, so the noise dominant, that's too much noise already. So it will not get an accurate result, okay. But at least for the first 5, 6, 7, 8 lags, so it produce for you correct results, okay, that means the first few autocorrelation matrix, they're all zero. Okay. It looks like a white noise until you look at maybe like 10 and beyond. And by then, the noise starting to dominate. Okay. So remember, it's a bivariate matrix. So you have more parameters to estimate. Okay. You have you have at least 4 times the number of parameters to estimate approximately. And so, noise starting to accumulate for these Young-Box statistics. So usually in practice, we do not look at a lag too large for these Young-Box statistics because you can see that even for white noise generated, and if we apply this test, you can see that beyond a large medium lag, maybe lag 10, it still produces inaccurate results. Okay. So there is the general difficulty for multivariate time series. Even for bivariate time series, you see traditional statistics start to break down quite easily if you don't have enough data. For the vector armor simulation, I have 300 data points. How about we can do another simulation? Eh? Let's increase the number of data points 10 times. So let's see what happens. Okay. So let's make it 3,000 rather than 300. And MQ M1 series, so it's still fine. Let's But how about the noise? No, that's better. No, I want to zoom. Okay. I hope you can see this. So now with 3,000 sample size, then it's enough data to conclude that, okay, it does look like a white noise. Okay. Yeah. There's several lags at the beginning, so it's still below the blue dotted line, but it is a white noise generated. Okay. And for majority, the Young-Box P statistics return a p-value larger than 5%, okay, above the blue dotted line. All right. So it's a good thing to remember multivariate time series is difficult. Even for bivariate time series, you need seemingly a lot more data to actually get analysis right. Okay. Traditional analysis, that is. Okay. Young-Box P statistics for white noise. Okay. Estimation of parameters, etc., etc. Okay. So, as a final thing, so I know I have only 4 minutes left. So let's focus back on a final thing. Okay, is forecast. So forecast, I can make it really quick. So in particular, I just want to talk about forecasting for VARP. Forecasting for ARMA model is similar actually. So if your xt is alpha plus phi 1 xt minus 1 plus up to phi p xt minus p plus epsilon t. This time I will assume my epsilon t is ID with mean 0 and variance covariance matrix equals to gamma. So it's IID white noise, okay? Not IID normal, but just IID white noise with mean 0 variance covariance matrix gamma. Then we can calculate the L step ahead forecast is the still the best L step ahead forecast with respect to the quadratic noise. Okay, quadratic norm is still the conditional expectation of xt plus L, conditioning on every information up to time t. And this is what? This is alpha plus phi 1 xt plus L minus 1 plus all the way up to phi p conditional expectation of xt plus L minus p. And then plot conditional expectation of epsilon t plus L. This is, of course, 0. Right? So this will be alpha plus phi 1 xt L minus 1 plus all the way up to phi p xt L minus p. And this is with xt bracket L equals to xt minus L. For L less than or equal to 0. Okay. So it basically gives you an iterative formula. Therefore, iterative. So you start off with first step ahead forecast, and then second step, and so on. Each time you replace with our so one step ahead forecast first is basically all we've passed the alpha plus phi 1 xt plus up to phi p x t minus p. Okay. Uh, xt sorry, p minus one, p minus one. Sorry, it's xt minus L minus P. So it's, if L is 1, this is 1 minus 1 plus P. Minus plus 1, sorry. Okay, so that's in the past. And then, so it's all in past data. So you replace L with 2. So xt bracket 2 will be alpha plus phi 1, xt bracket 1, which is already calculated. Then everything else follows. Okay, so it's iterative. Okay, so in scalar, you can do this. Okay, but in a multivariate time series, the iterative scheme seems to be easier to handle computationally, at least. Okay, so people will talk about this iterative scheme. All right. So I think time is up. So next lecture, I will talk about Grandeur causality. Okay, and then other aspect of multivariate time series and factor modeling. Okay, if we have time. All right. I'll see you guys next time. Okay. For those in seminar, let's use another link I've sent you. Okay. So I'll see you guys. Okay.